So namaskar. So today we will talk about. So we will continue our raster data processing. So in yesterday's lecture, I explained how do we read a raster image using GDAL. Then using Matplotlib we visualized the image and so on. So today we will start with we will learn how do we write a raster using GDAL. So, just for quick review of yesterday. So, how do we first thing this is the this is Jidal's raster data model. So, whenever you open a file, it returns you a data set. So, the data set will contain may contain one or more number of bands plus geotransformation is information associated with that image. So with the help of this geotransformation information and projection, we can project that image on a map. Plus every band will have some data array and corresponding maybe one or more overviews of that particular band. So the process of opening an image was first we need to call the jidal.open function and pass it the name of file which you want to open. Actually, Jidal supports multiple raster format, GeoTIFF, NV, or what call ADAS Imagine. So multiple more than 80 raster formats plus vector formats as well. So once we call the jidal.open method open, then it returns us a data set. So from the data set we can query the projection information, raster size, how many bands are available in the image, all type of information about the image plus the data of some particular band. So now next, once the data set is read, then we have to fetch some particular band. Suppose image has 3 bands, then you can fetch all the bands by calling get raster band function. So get raster band, it takes an argument band number, which band you want to extract. So that way we can proceed. So this way we can put it. Then with using Matplotlib we can visualize the data. So our today's task is now suppose we have some data. Now how do we convert that data to a raster image? So actually basically there are two techniques using with Jidal. There are two techniques for creating file. One is you can use create copy method and another is create method. The create copy method involves calling the create copy method on the format driver and passing it a source dataset that should be copied. So when you should use create copy, suppose you have or you already have some raster available with you and you want to do some processing on that. So you have a raster, you did some processing on that and you just wanted to save it. So create copy method should be used in that place. So then in that case, all the projection information, bands, everything will be copied from the source to the destination. Then you apply some processing on the data and then data can be written back to the file immediately. So there you can use create copy. And when you don't have any data to copy it from some other source, then you can use create. So in the create method, you need to explicitly pass. Actually, when you are using create copy method, everything from the source file will be copied, and whatever you do the processing and write back. But when you are using create method, then you need to explicitly specify like what is the metadata you want to write, what are the raster data, what are the projection, trio transformation, and like how what is the width of your image, height of image, which data type you want to use. So everything you need to explicitly tell to the driver. So then driver can create a data set for the parameters you specified. But in the case of create copy, it just copies from the source file. So let us see with example how do we use it. So for writing a data set, first anyways, like yesterday, I am just defining a file format variable. Suppose if I want to copy or create copy a GeoTIFF file, actually I can copy any other file. So we'll take an example of GeoTIFF file. So first I am defining a variable with name file format. So I want GTIFF. So GTIFF actually is the short name for the GeoTIFF, as we see. So yesterday actually the short names for all of the different files are available at this link. So here if you open it, so So actually, suppose these are the different raster formats supported by GDAL, and these are their short names. So suppose if you want to create a raster image using AIG format or ARG, these are the names and these are their short names. So you need to refer to this document and correspondingly pass the short name to this, whether GTIF means GOTIF, HDF4, HDF5, these are the short name for those formats, so that you can find from this link. So just I wanted to write a GOTIF file, so I have defined a variable with name GTIF. So now the first task is we have to create a driver. So actually there are multiple raster formats, so every format will have every format is different from others. So in GDAL, for handling every format there is a driver. So first thing we need to get the driver for that particular format. So how do we get a driver? So GDAL has a method function by name get driver name. So you need to pass driver equal to GDAL dot get driver name, and you have to pass it the argument of short form of the file description. So like for GOTIF, so I am casting here file format GTIF. So this will create a driver for handling GOTIF data in GOTIF format. So now once a driver is created, you can just get some basic information about the driver. So short name, whatever we pass GTIF. Suppose if you want to get the long name of the driver, you can call driver dot long name. So it gives the complete name. That's GOTIF. Now by default, you can check what metadata is available in the driver. So driver dot get metadata gives you the capabilities of driver. So it returns you a dictionary. So this is the basic metadata available with this. So what it says that dcap dot create. So with this driver you can create a new file, or it has the capability to copy also. Actually there will be multiple formats which may support creating some formats may support just reading. For some formats in GDAL support for some formats only reading. For some formats it supports both reading and writing. So just by seeing these parameters you can make out that create. So if it says it has the create yes, means you can write a file in that particular format also. If create is no, it means that GDAL that particular driver doesn't support writing. So you cannot write a file in that format. So like create copy, it supports create copy, open, raster, virtual IO. So these are the different things and which all data types you can use. So this is the information about that driver. Once the driver is created, now suppose let us see how do you use create copy. So here I have a file with a list3 image, list3 band 2 image available. So what I will do, I will copy this using this file. I will we will read this file first, then do some basic processing on this file and write back the processed file to some other file. So I am creating here a source file. This is the name of the source file, and this file I want to save it as using another file name like output raster1.tif. So I am defining a variable destination file name that I just want to name it output raster1. So first thing I have to open the source file. So first I have to open the file for reading. So what I am doing, source ds is equal to GDAL.open, then this source file. I am reading this file. Anyway, this driver is already created. We need not do this. So next, now we are using create copy. So for this we have to call on the driver. So once the driver is created, already we have created a driver. So on the driver variable we have to call the create copy function. So driver dot create copy. So it takes two arguments. First is the destination file name. So what destination file name you want to give, and second is the source data set from which you want to copy. So two arguments we need to pass it. So then it will create us a destination data set. So let us see if I print it. So if it has successfully created dst_ds, it says a data set got created. So now everything from this source file has been copied to the destination data set. Now like yesterday I said, now suppose if you want to see the data, what is the data in our source file. So now source data set dot read as array. So So it will, we will, with this will read the data. So now if you want to see the data, so this is the data available in our source file. Now we will do some processing, like suppose if we want, this is a number, this is a two-dimensional numpy array. Now in this data you can do any processing, you can add something, you can add some bias, subtract, multiply, or so suppose now what we are doing, we are just applying an invert operation. So this data we will just invert. So ones will be converted to 0 and zeros will go to, will convert, this number will be represented in binary. So all ones will be converted to 0 and 0 will be converted to 1. So just we are, what we are doing, np dot invert data. So our simple processing, we are just inverting the data. Then we are assigning to a new variable called inverted data. Now let us see how the data and inverted data are there. If I just, we are can using, so this is the data in our original file, and this is the inverted data. So here you can see that all the dark areas have become brighter and brighter areas have become darker. So this is the inverted image. So we have read a band to list 3 band to image and inverted the data. Now we can write this data to a new file. So anyway, we have created a destination data set. So now what we need to do, we need to fetch the band from our destination data set. As I explained, destination data set also will have the, if our source image was having one band, so destination data set all will also have a band. So now we need to just fetch the band using get raster band, and on that band we need to just write that array, write the data. Now out band dot write array, instead of data we will write here inverted data. So once this is done, if it is returning 0 means the writing is complete. Then on the band we need to call the function flush cache. If you don't call the flush cache, what happens, the data doesn't get returned to the disk. So for that we need to call flush cache on the function. So with that it gets written onto the disk. Then finally we have to delete destination data set. So we have to we are closing the file. This is similar to the closing file. So how do we close the data set? Either you can call del dst underscore ds, or you can assign it to none. So both the ways you can be doing. So after writing, we should close the file. So this way, so anyway this was already deleted. This way we can, so we can copy contents from the file, modify the, or apply some processing on the data, and we can write back the file with other name using create copy method. So now if you will see in my directory, there will be a file with name op raster 2. So suppose if I delete it, so here we have given the name output raster 1. So it says it is open. So there is a file here. Now suppose if you want to visualize, you can visualize it using QGIS or any other software, or even here itself we can read the data and visualize. So this way we can, whenever the requirement is that you already have data, you want to do some basic processing on the data and write back, there you can use create copy. Now second method is create. Now when you don't have any other information, like you don't have a source file to copy, you have data in some form, you have data in maybe, so you have collected data in some format, maybe your text file or some other format, and now that data you want to convert to a raster format. So there we can use create method. So for situation in which we are not just exporting an existing file to a new file, it is necessary to use create. So whenever you don't have, we are not exporting the existing file, so there we need to use create method. So to create method, for using create method, we need to know already what is the size of image, width of the image, height of the image, how many bands are there, what is the data type of every pixel's intensity, that we must know, we must know, and that those parameters we need to pass to the create method. So here what will I do? I have a CSV file here, rainfall. So this is the rainfall data over the Indian region for some previous some date. So here actually what every cell has a, this is a grid. So in this is a description of the file. I have a CSV file containing the daily graded rainfall data set over the India. So I have the I have a rainfall or rainfall data set over entire India. So so this is the first data in the record is this is like at this latitude 6.5 degree north and 66.5 degree east. So what was the rainfall at this location? Then next is like 6. We are here if we are going by longitude wise. So 0.25 degree longitude and 0.25 degree latitude. So each cell represents to 0.25 degree by 0.25 degrees square cell. So this is the rainfall at that particular location. So like this we have a text file describing the rainfall data at every 0.25 by 25 degrees grid. So now this rainfall data, because this is in textual data, now numerical data is, but it is in ASCII format. Suppose if you want to visualize that how rainfall occurred all over the India by just seeing this text file, it is quite difficult. So if we can convert it to image format, so that will be easy to visualize. So now we'll see that how do we convert this to this particular data to a raster image. So here every cell, this every value is corresponding to a grid of cell of 0.25 degree by 0.25 degree. So this entire file covers latitude ranges from 6.5 degree north to 38.5 degree north. Latitude 6.5 to 38.5 north, and every cell is 0.25 degrees. Similar way, longitude it covers from 66.5 degree east to 100 degree east. Same resolution is 0.25 degrees only. So this entire data set has 129 rows and 135 columns. So now what we will do, first I am defining a like this data set. I have this file name is rainfall.txt. I am saying that okay, a variable source text file rainfall.txt. Then this destination file name I want to give rainfallindia.tif. Now I want to convert it to rainfallindia.tif. Now like similar way, first we have to create a driver for this data format. So same thing, driver equal to gdal.get driver name. This function we need to call and pass it the argument which format we want. So suppose we want to write geotiff. Then next, earlier we used driver.create copy. Now we have to use the function driver.create, because now we don't have any explicit source file to copy. So first we have to call driver.create. So this takes these arguments. First is the destination file name. So the data will be returned to this particular file. So we have a variable rainfallindia.tft. Then x size, so width of your image. So as I told that width of our image is 135. So our image has 135 columns. So x size is equal to width of your image, because in x direction will be the width of image. Then y size is equal to our number of rows or width of our height of our image. So that is 129 pixels vertically. So y size we are passing as 129. And we have just a temperature data. So our image will have a single band. So our image has a single band. And band is equal to 1. Then E-type. E-type is the data type. So our data type, actually if you can see, this is a floating point number. So all the numbers are real numbers. So we need to convert it to a floating number. Instead of int 16, we need to pass it gdal.gdt. So float 32. So this will create a destination data set. So what arguments we need to pass to the destination to create method? Destination file name, width of your image, height of your image, how many bands you want to create, and what is the data type of each pixel's intensity. So this is a, we want to use 32-bit floating point number. So this, then it creates a destination data set. Now we need data to fill into the destination. So our data is available in the text file. So first we will get the data from this text file. So how do we read the data from this? This is a CSV text file. So in NumPy library has a function called load txt. So first we will call np.loadtxt. So this will read the content of the text file. So np.loadtxt takes an argument like source, like file name, and what is the delimiter for a separate delimiting two consecutive values, and then what is the data type of your that you want to interpret in from your text. So np.loadtxt will read the data from the CSV file. If it has run, let us see that how is the data. So this is our data. You can see that rainfall was having minus 19,1999, and somewhere some values are there. Actually minus 999 represents no value. It means that data is not available for this particular cell. So this way now we have read the data from our text file. Now what we have to do? We have to copy this data to our band 1. So first what we will do? We have to fetch the band from our data set. So same method, destination data set dot get raster band, and pass it the argument band number. So which band you want to write? So band 1. So this will fetch us the first band from our destination data set. Now suppose if you want to add some metadata also to this image, so that also can be done. Now suppose if you want to add to this band some, like when this data set was created, some, like if you want to tell some more information about your data to your user, so then that all information can be written. So suppose now here we want to just to write some, like when this data was created and what is some scale factor, offset and all. So for that we need to create a dictionary first. So for metadata we need to write in the form of key value pairs. So so here what I am writing, I am creating a dictionary. So first key in the dictionary is date of creation. So I am writing the current date, then some scale factor and any other parameter if you want to write, like unit of rainfall. Suppose you say that it is in millimeter. So that information you can write so that the user can interpret it. So we have created dictionary. Now if you see this dictionary, this created a dictionary. Now on the band we need to call the then set metadata function. So band dot set metadata if we call and pass it the dictionary of key value pair, then so that it will set the metadata for that particular image. So with this we have written some metadata to that band about our data that we wanted to do. Now actually there is one more thing, like set no data value. Suppose in our image we have for certain locations we don't have data available to us. So that you want to specify, like, okay, like missing values. So we want to indicate to the user that if you encounter this pixel intensity, man, this is a missing value. So for that there is a function called set no data. So now here we have minus 99 minus 999 as a missing value. So we on band dot set no data value with this function we can set the value of no data. So whenever user encounters minus 999, which is a missing value. Now this is done. We have fetched the band, set some metadata into the band, and we have set the no data value. Now this is the time to write the data. So our data is available in the data variable. This is a two-dimensional NumPy array. So similarly, like yesterday we were reading, now we have to write. So band dot write array and pass it the NumPy array, two-dimensional NumPy array. So band dot write array will write the complete numpy array to the band. Now actually this metadata was specific to this particular band. Suppose our image is having 3 bands and we want to save metadata band wise. So band 1 might have some different metadata, band 2 might have some different data because band 1 may be red. So their scale factor, like for converting that to reflectance, or like if it is temperature, so some different formulas or any other information. So that this metadata was specific to that band. Now there may be like you want to have some metadata that is common to entire data set. So that also we can write. So like here I have created a new dictionary like new metadata. So that will be written for the entire data set. So this previous data set was specific to that particular band. So this data belongs to the entire data set. So like here you can write date of creation, like organization which created this particular data set, then what is the processing level or any other information which you want to provide to the user that is common to the all bands. So that can be written directly on the data set. So there we need to call this set metadata function on the data set. There we called it on the, we fetched the band on the band we called the set metadata function. Here we are on the data set itself we are calling the metadata function. So this way we can write the data set that is applicable, metadata that is applicable to the entire data set. So once everything is done, anyway we have written the data. Now again similar thing like flush cache and free the memory. So this is done. Right now if you can see that there is no file with name Rainfall India in this folder. So anyway it has created a 0 size rainfall file that was previously. There is no data in this. You can see this is 0 KB file. Now just I do the flush cache and now the data will be written to this directory. Now you can see that there is 69 KB data is available here. So now let us visualize this data, that how the data was there. Now just we will try to read the file using GDAL. So again ds dot open GDAL dot open. Then on the data set if we call the ds dot get metadata function. So here we can see that on the entire data set we had written this metadata, date of creation, organization and processing level. So now it returns us back date of creation, organization and processing level. So this way we can get the data, retrieve the metadata which is available on the data set. Similar way, suppose now we can fetch the band like by calling ds dot get raster band and then call get metadata function on the band. Actually here I have combined 2 steps, otherwise you can fragment into 2 as well. So once you can call this, then band dot get metadata. So this returns like date of creation, scale factor, unit, that whatever data set we have written on the band. So this way we can see that data set plus band also. So all individual bands might have different metadata. And then we had set a no data value also. Now suppose we want to retrieve what is the no data value. So that we can do get raster band anyway band dot get no data value. So anyway we had set minus 9999. So it says minus 999. So after this is done, this is now suppose if we can open this file in any software as well. Like suppose if I want to open it in QGIS. But I think if you if you have seen it carefully, because we had not written any transformation information with the image. So the data is stored, but there is no transformation information associated with the image that we have written. So if you open it with any other software, it will complain that there is no special information is not available on the image. It will not be able to project it on the map. So in the next, we will see that how do we write projection and transformation information with the image so that it can be projected on a map. So for writing an image using create method, you need to first create a destination data set in which you need to pass the name of file, what name you want to give, width of your image, height of your image, then how many bands are in your image, and the data type what you want to use for your image. Once that is done, then you can fetch all the bands one by one for your image and then write on that band using band.writeArray function. You can push your data onto that image for every band. Plus you can write some metadata. So then finally you have to flush out the cache and delete the destination data set and free the memory. So if I see here, so suppose if I open this rainfall, so you can see that the image is flipped. So I will explain you later on why the image is flipped. So this we created the rainfall data for our, from the text data we converted it to a raster image. So if we see here information, by default it has associated the metadata set. So we have not attached any projection information to the image. So now let us see that. Now we will see that how we write a geo-referenced raster. So we will attach transformation plus projection information also with the image. So for that, first we need to create a spatial information. So for creating spatial information, we need to GDAL has a OSGeo module has a package called OSR. So first we need to import the package OSR. So I will delete this file. Now suppose anyway we had opened the file ds again. So okay, let's write how to write a georeference raster. So first thing we need to create a spatial reference system. So for that, first we need to call import the OSR module. OSR module is for handling spatial references. So on the OSR, first we need to call OSR.spatial reference. So OSR.spatial reference will create a coordinate reference system. So CRS. So first we need to call OSR.spatial reference system. Now we need to tell whether what the CRS is projected or geographic coordinate system. So anyway, first we will see that we have the values of latitude and longitudes. So our projection system is going to be a geographic coordinate system. So suppose if you want to make it a geographic coordinate system, actually GDAL itself, it has a function called set well-known GeoGCS. So actually it's by default, if you like WGS84, NAT27 and other geographic coordinate system, it has a function for setting that. So CRS dot set well-known GeoGCS. So WGS84 we can set using set well-known GeoGCS. So once this is done, if it returns 0 means successfully it created the CRS. Now let us see the description of the CRS. So we can see it as yesterday explained. So CRS can be written in multiple formats, maybe WKT, PROJ4 string or some other format. So here if we see that, so it has created a CRS geographic coordinate system with WGS84 datum, authority, these things. Like similar way we can print it in some other format. Export to PROG4 string, suppose if you want to display it as. So this is the textual representation of our projection system in different ways. So WKT, PROJ4 or So once our spatial reference system is created, now we need geo transformation information. Once this is created, so anyway, as I explained initially, that our data starts from 66.5 degree east. So the coordinates of our 0 pixel are 66.5 degrees. So this is the affine transformation information. A longitude of 0th pixel, then the pixel size in x direction. So as I explained that every cell is a grid, every cell is of square of 0.25 by 0.25 degree by 0.25 degree. So this is our pixel width in x direction. Then rotation, anyway our north is up in our image, so this we are passing at 0. Next argument is the latitude or y0 of our 0 pixel, latitude of our 0 pixel, so it starts from 6.5 degrees, and this is the rotation. If north is up, this will be also 0. This is the pixel width in y direction. Actually now our data is such that the 0th line is, so actually in this case y is increasing, so our first line represents, so as if you see the detail of this, so the data at first line represents the cell 6.5 and 38.5, 6.5 degrees north, and actually second line corresponds to 6 first line is correspond to 6.5 degree north, and second line it is 6.75. So actually in our actual raster data set, actually y is increasing, so our origin is at bottom of our image, so y value is increasing. So pixel width in y direction I have given, instead of minus 0.25 it is plus 0.25. Actually the first row is corresponds to latitude of 6.5 degrees, second row corresponds to 6.75, and so on. So the y also is increasing, so the origin of our image is at bottom left, sorry. So once we define the transformation information, now again similar way, now we have to read the data from our text file. Then suppose we have to write it to whichever file we want to write it, like India _ georeferenced, we will say GCS. So instead of writing to the GOT format, now we will write it to the IMG format. So now I have given it a name, India range GCS.img. Next, say now similar things. First we have to get driver is equal to gdal.get driver by name. For actually IMG format, the short name of the driver is HFA. So we need to pass it get driver by name HFA. So it creates a driver. Then same thing like driver.create. So driver.create will create a destination data set. There we need to pass the same arguments: destination file name, width, height, number of bands, and data type. Our data type is 32-bit float. I'll just copy from here. So once created a data set, now we need to, now in the previous case we have not written any projection and transformation information. So now on the destination data set there is a function called set projection. So with the set projection we can set the projection information. So destination data set dot set projection, but it takes projection information in WKT format only. So our CRS we have to export to WKT format. So CRS dot export to WKT. So this will set the projection. So similar way there is a function called set geotransform. So if you set destination data set dot set geotransform, it will set geotransform information on the image. So with with the help of these two functions, we are setting the projection and transformation information of our image. Next, this is the same thing. Destination dataset dot first we are getting the raster band and we are setting it the no missing value as minus 999. Then this is the same thing that we have done. Now we have same thing, we are reading the data from our rainfall.txt file. Then the function band dot write array. So this will write the data to the image. And finally we are flushing out. So everything is same, only thing here we have added two more steps, set projection and set geotransform. With that, projection and transformation information is stored. Now let us read the image and confirm that whatever we have written, everything has gone there properly or not. So if I see here, there will be an image with name rainfall india.gcs. So this is the image. If I open it, so here you can see that this is our image, and if you want to get information about this, you can see that this is the image rainfall EPSG WGS 84 EPSG 4326. These are the extents of image whatever we set in our geo transformation. So here we can see that we had set the image like 66.5 and 6.5, and then these are carrying 100.25 and 38.25. Then width 135, 129, 32 bit float, and so on. Then this is the width and this is the pixel size 0.25, and actually it has converted it to internally it has converted, I think, so it is showing as minus 2.5, though we have set it 0.25. Now let us read this file using GDAL and confirm that whatever we have written is correctly wrote. So now again same thing, we will just read the file. GDAL.open, then our destination file name is okay, correct. So similarly we can read. Then suppose if now we want to get the projection, whatever we have set, whether that is only got set on the image or not. So if you see, if we ds.get projection, if you do, that's done there. Now in this previous image we had not set the projection. So if you want to confirm that, then we can call this file rainfallindia.tf. And here we say that it said there is no projection. So we had not set any projection to the image, so it is not showing any projection. So now we will change it back to our original image. So then I say this is, then similarly I can retrieve the transformation information. So if I see the transformation information, whatever we had written 6.5.250, this is. Now if you want to retrieve the data, so similarly we can retrieve the data. And now if you want to visualize the data, so this is the visualization of our data. So anyway you can see that, and though we had set the values minus no data as minus 999, but matplotlib has not taken it. So suppose if you want to display that no data values with white color, so what we need to do, because here it is not quite clearly visible, so this is white. So what we can do, we can use a masked array. So what we can do, we can first we have to get the no data values from our data set. So I will say that no data is equal to So we have set the no data value on the band. Or band dot get, band is ds dot get raster band. ds dot get raster band 1 that get no data value. So with this I retrieve the value of no data. So anyway, I know here it is minus 99. Suppose if you have got a data set from new some other source, then you don't know what is the value. So you need to query what is the no data value, and then we can create a masked array. So I can call numpy has a dot ma, that is the masked array. Masked array is actually the, so you can mask some values as ma. I will say, now what will I say? Masked data I will say. So all the no data values we will hide from the other things. So masked data equal to, I will call ma dot masked equal. So from my original data, all data is with value, no data I will hide. So now if I see it, now you can see that the all no data values got hidden. So those are masked, and this has become quite white. So actually what here I have passed the argument at origin is equal to lower. If I don't pass it origin equal to lower, what will happen? The image will be flipped. Why it is happening so? Because our in our text file original data. So actually the values of y starts from here. So actually value of y starts from here. Actually on our data, our first data is for this latitude longitude. Then it is in reversed order. So our origin is starting at lower point. So we need to pass it as origin equal to lower. Here our origin doesn't start from the top of the image. Our origin is starting from the bottom. So the image will be flipped. But if you can see here this is a function. So this is the thing. So we are just inverting the image for display, because otherwise, because over here in geo transformation our values of y are increasing. So had it been minus 2.5 like top to bottom, then it would have been minus. But because our values are bottom to top, so values of y are increasing. So our origin starts at the lower corner. So we are saying at 0. If you open this particular image in any GIS software, by default it will show it correctly. So once it is done, then we have to delete it. This way, this is we have seen 3 ways. Like we can, how do we create a raster data set? First, we can either you can use, if you have already some source data set to copy, so then you can use create copy method. Then second method is using create. But for create, you must know how many bands are there, and what is the width of your image, height of your image, what type of data you are going to write. This is done. Then with data you need transformation and projection information also, so that the image can be projected on the map. So with the help of projection and other information, this way we can create a raster data set. Now let us see that our next task is stacking raster bands. Generally, actually, if you download data from any satellite provider like ISRO, NASA or somewhere, so what they will do, they will not give you a RGB or any composite image. So they will give the data in form of, like, for every band there will be a separate image. So now from these for red there will be red band image. So suppose if this is the data I have. So whenever you download the data, so they will give for every band separate image. Now stacking means we will combine the red, green, blue or any other combination of bands and create a single composite image. So suppose you downloaded the data and you got 3-4 bands together, separate images. Now you want to visualize it in true color or false color composite of that image. That is called stacking. So let us see how do we stack multiple band images together. So here what I am doing, I have 3 images in this folder, Haridwar and 21st February 2018. So this is my image. So these 3 bands I will combine together and create a composite image. So first I am defining file names which I will be stacking and make a composite image. So what I am doing, what we will do here, we will loop over the list, our list of files one by one, read the files one by one, and so how do we stack together? So first what we will do, first we will loop over the files, get the data from each of the file, then we will create a destination data set. Like suppose if you know that we have, so let us see one by one. So what I am doing here, first I am creating an image data list. So what there, first we will loop over all the files one by one. So for file in files, first we are opening the file for reading. So gdal.open file. So if I just hide all these, so what this function does, it will loop over all the files. So this is looping over all these files together, band 2, band 3, band 4. Okay. Now what we are doing in the next step, we are first opening that file. So we are calling gdal.open and opening the file for reading and reading the data from that file, whatever pixel intensities are there, and that every data we are appending to a list. So the list will have now 3 elements. Its 0 element, its 0th element will be the data for band 2 image, first element will be the data for, so this will be nested, second element is the data of band 3 image, and so on, and third. So this way we have, so it could not read the image, I think the names of image have. So once this is done, now if we see the image data list, so this is a list where we have appended all the data together. So you can see that image data is a list. It has 3 elements. So image data 0, if you see, this is a list if you index anything. So image data 0 has the data of first image. Then image data 1 will have the data of second image. Image 3 will have the data of the third image. So this way we have read the data from all 3 images and pushed them into a list. This is true. Next word, now let us visualize the images. So we will see that how the data is there. So this is the data for every band. So this is band 2, band 3, band 4. These are the three bands. Now we will combine three bands together and make a composite image. So now the things remain similar to that. Now what we will do, we are giving our the we are first creating destination file name. It's tagged RGB image.tif. So that will be the name of our destination file. Then, anyway, as I explained that we need now we will use the method create, because here we cannot copy directly because our source files all having single bands only. So but we want to create an image of three bands. So what we are doing, so we are just first, because all the three images are of the same satellite or same scene, they are of same scene, so every image will have same height and width. So first we are calculating the width and height of the image. So our anyway image data is a list. So from image data 0 dot shape, if we query, it will get us the width and height of our image. So this will be the height or width of our image. Suppose if you want to print. So we get the height of and width of 1151, 1151. Now first thing what we do, anyway now we have read the data from all three images. Now we need to create a destination data set. So the procedure is similar only. First we are calling driver get driver by name, and suppose if you want to create a geotiff image, so gtiff, then we have to create a destination data set. So destination data set, again same, we are creating using create method. So destination data set driver dot create. So then we are passing it the argument like what is the destination file name, width of our image, height of our image, then how many bands are there in our image. Actually we are combining three bands, stacking three bands together. So number of bands, then data type, unsigned integer 16-bit integer. Then we have to set projection and transformation information. Otherwise, if you open it in any other software, it will complain that special information is missing with your image, and so it can draw but it cannot project it on the map. So once we created destination data set, now we are setting the projection. Anyway, in the previous slide we said that how do we create projection and transformation information, but here anyway we have read an image. So this DS one by one. So this we are just copying transformation and projection information from this data set directly. We are not creating here our projection by our own, and transformation also we are copying. So destination data set dot set projection, we are getting it from our last file which we opened. DS will contain the file, like when it will loop over. So DS will contain the information of the last raster. Anyway, these all images represent the same area on the earth, so they have same projection and transformation information. So either of the file we can take. So we are taking, because this will, when it is looping over, this will contain the information of the last raster which it looped through. So we are copying it from that. So set projection, get projection, and ds.get geotransform, setting it using set geotransform. Once we have set everything on the destination, now suppose if you want to see that what is done, you can call get projection. So instead of this, we can call dst underscore ds. So now our destination data set is ready. So now we need to copy the bands data. So anyway, in your image list, we have the data for all three bands together. Now we will start looping over all the bands one by one and start copying the data. So here we are, first thing is we are running a loop for I in range 1 to 4. Actually, as I explained yesterday, JIDA's band start from 1. So for I in range 1 to 4, because our image has 3 bands, so it will go from 1 to 3. So first we are fetching the band. So destination data set has 3 bands, but there is no data in those bands. So the values may be 0, 0 only. So first we are fetching the band dot get raster band I, and then we are writing in that band the data. So from image, anyway, our image data list has all the data. So image data, here we are passing the index as I minus 1 because list index starts from 0, but band in Jadal band index starts from 1. So here we are passing as 1 and next will be I minus 1 because first band data is stored at in list at index 0. So band dot write as array. This is done. It means data is run. Now finally on we have to call the flush cache method and then delete the data set. Once this is done, there will be a file created here in this folder using the name stack rdgv img.tif. So actually my working directory was this, so it got created in this directory. So this is the stacked rgb img.tif. Suppose if I delete it and confirm. So this was only the file. Just create an image of this folder. So I will just change my working directory. To this folder, and I will take the names from this. So I'll just run over it. Right now you can see that there is no file with stacked name. Then once done, it creates a file. Anyway, it has not created yet. So after this is done, there will be a file with name stacked. So stacked RGB has done, but there will be no data yet in this image. So I am looping over and writing the data flush cache and destination data set. Now the file is created. Now this you can see. This is 7.5 MB file is already created. So this way we can stack the bands together. Now let us see how the image looks like. What will the composite image? So first that, so either you can open it in software or you can do it yourself. So we have combined 3 bands together. So I'll call so here you can see that this is a 3-band image. Anyway, this is not a true color or standard false color composite. This is some false color composite. So that same image you can read from here also. Anyway, destination file name, we have already defined the variable. So now we will just open it using readall. We have first now written, now we will read it. So then we are reading the data, and with matplotlib if you visualize it. So this is the image. So you can see that both, it is closed here. So this way we can stack different bands together using Jidal. So for stacking, what we need to do, first you can read all your individual band images get the data and put it into some list or some other way, then you know that after thinking, okay, our destination image must have this many bands. This will be the projection info projection. This will be transformation of our image. Then copy those transformation and other information from the any of the source data set and create a destination data set of the same size, but number of bands will differ. So loop over the data one by one and copy the data there and ultimately push it there. So this way we can stack together all these images. What has happened here? Actually, Jira, this band 2. So by default, so band 2, list 3, band 2 is green band. Band 2 is green, band 3 is red, and band 4 is NIR. So what has happened? So green has gone to the red. Green has gone to the red, and red has gone to the and NIR has gone to the red, and swir band has gone to the blue. So you see some false color composite like this. Now instead of this, suppose if you want to reorder, suppose if you have a stacked image and you want to reorder the bands in your image, like whatever image was available in whatever band, if you want to reorder the bands of your image, band 1 you want to push to band 2, or band 1 and band 3 if you want to swap or something, like you want to reorder the bands in your composite image, that let us see how do we do it using. Now this is our image. Now we will reorder the bands of this image. So this is the name of our image where you have changed it. So now then later we will name it as reorder.tif. So for that, what there is a utility in JDAL, that is translate. So with you help of JDAL.translate, we can reorder the bands of our image. So what argument does the translate function takes? So JDAL.translate. Then first you need to pass the argument destination file name, and in which file your data will be stored. So we are saying that RGB reorder.tif. Then second argument is source file, which file you want to reorder. So this is the source file name. Then the band list. So how do you want to reorder the bands? So what does it mean? 3, 2, 1 means from our source image, whatever data is available in the band 3 of the source image, that will go to the band 1. Whatever was in band 2 will remain second only, and data from the first band will go to the third band. So actually we are swapping band 1 and band 3. So from our original image, band 3 data will go to the band 1. So this will be the first band of our destination image, and second band will contain the second band only, and third band will contain the first band. So band 1 and 3 got swapped. So now suppose if you see the data and plot, now you can see that our image after swapping band 1 and band 3 got changed this way. Similarly, suppose you can change it to, like if you change 1, 2, 3, it will not be anything. Here you want to put band 1 only. Here you want to put band 3 and band 2. So this way you can reorder your images, and different types of false colors composites you can create. So this way you can reorder your bands very easily and create different false color composites. If your image has some 10, 15 bands, so just using JDAL.translate, you can reorder your bands and create different kinds of false color composites very easily. Then ultimately once this is done, you can close it. Now we will see that subsetting a raster. Suppose you have a big raster and you are interested in some particular you are interested in processing some particular area of the raster, particular subset of the raster. So you know the coordinates of your area, like my coordinates vary from 78 degree north, 78 degrees to 79 degrees east, and 29 degree north to 30 degree north. So you know the coordinates of your area of interest. So from you have a big image and you want to just extract that the data for that particular area of interest only. So that we'll see that how do we subset an image if we know its real world coordinates. So I will take an image or list 3 image only. So I am just changing my working directory to this. Haridwar L3H44. So here already one subset file is there. I will delete it. So I am reordering this. I will subset this file L4H44M01 21 February. This particular file I will take. So first thing what I am doing, or similar thing whatever we have been doing. So first we will open the file for reading. Now first get the geotransform. So first suppose we want to know what are the extents of the image. So as this was explained in my first lecture, previous lecture, so we can get the extent of our image. So these are the 4 corners of our image. Upper left corner has the coordinate 77.99 to 30, and these are the 4 corners of our actual image. Now suppose if you are interested in, we want to get the area in these extents only. So longitude varying from 78.15 to 78.20 and latitude varying from 29.75 to 29.80. So we just want to extract this much area from our original image. So what do we have? I have defined a variable subset extent. There I have given the extent which I want to extract my image for. Now what I need to do? First I need to know that these pixel, what is the line number and pixel numbers for these extents in my image, because image finally it will be in line number and pixel number. So first I need to calculate what will be the line number and pixel number for these coordinates. So for that, like yesterday I explained a function called Judal.apply geotransform. With the help of apply geotransform, we can convert line number and pixel numbers to the real world coordinates. Now this is the problem is just reverse. We have the real world coordinates of our area of interest. Now we want to convert them to the image coordinate system. So we want to get what is the line number and pixel number of those latitude and longitudes. So for that, first we need to convert in inverse geotransform. So anyway, we have got the geotransform of our image. So we will just get the inverse geotransform of our image. Then on that inverse geotransform, we will call the apply geotransform. So on the inverse geotransform, if you call the geotransform, with that we will get the coordinates in image line number and pixel number. So suppose for this we want to know that 78.15 and 29.75. These are the top corners of our area of interest. So we want to get what will be the pixel number and line number for this pixel in our image. So we can get the offset. Anyway, these offsets will be in a floating point number. Actual but line number and pixel number will be integer. So with the map function, we are converting these offsets to integer. So it is saying that these two coordinates starts at line line number 686 and pixel number 908. Similar way for other extents 78.20 and 29.80 also we can calculate. So with that we will know that how many lines and how many rows and how many columns we need to extract from our pixel. So first what we have done? So we are calculating line and pixel offset for our first corner, top corner. Then similar way on this is the top left corner. Similar way we will calculate the line number and pixel number of bottom right corner. So similar thing sub extent 1 and 2. So with this we got that okay. So our area of interest starts from line number 686 and pixel number 908 to line number 908 and pixel number 1131. So with these two coordinates, we know that how many rows and columns we need to copy. So we can calculate how many rows. So 908 minus 686, y offset 2 minus x, y offset 1 offset will give us how many rows, and similarly we can calculate how many columns. So what we have done, our areas of interest, we know the coordinates of our area of interest. So we have converted those latitude and longitude to pixel number and line number for those top left corner and bottom right corner. So we got the row number and pixel number. Now we subtracted them, then we got how many rows and pixels lie in our area of interest. So we calculate, so we know that now we have 232 rows and 222 columns. So now we need to copy 232 rows and 222 columns starting from this row number and pixel number from our original image. So anyway, we had opened our image. So now we will call the read as array function. So as I explained yesterday, if you call the read as array without any argument, so the entire image will be read. Now instead of that, if you want to read some partial portion of your image, anyway now we have calculated that our area of interest starts from 686 and 908. So we will passing it 4 arguments, x offset and y offset, from which portion of the image to start reading. So anyway, this is calculated. Then 4 arguments are how many columns and how many rows we want to read. So it takes 4 arguments. So we have passed it. We are passing it 4 arguments, from which offset to start and how many rows and columns to read. So this will get us the data for our area of interest. Now let us plot the data. So ds.read_array will give us the entire image, and our data is the data in our area of interest. So you can see that this is the entire image, and this is the subsetted area. So the image size here is 1151 by 1151, and this is the subsetted portion of our image. So now suppose this subsetted portion you want to save to a different file. So what you need to do first, because from your original image now just you need to change the extent of your image, because now the subsets extent are different, and but the other things remain same, only resolution remains same, only extents of our subsetted image are changing. So we will just copy everything from our source file and just change the extent and write it to the file. So, so first we have copied the geotransformation information of our original image. So now x0 and y0 only are changing. So GT subsets 0th in 0th portion, x0 we are putting new subset extent, and y coordinate y0 we are putting whatever new subset extent is there. So that's all we have changed. So now the extent of our subset are 78.15, starting from 78.15, because this was our area of interest, 78.5, and the resolution remains same only because we have not resampled the image, and north is up, and similarly this is the y starting coordinate of starting latitude of our area of interest, then pixel resolution. And similarly now everything we will create a destination data set. Either we can copy everything from the source data set, but what will happen there, the number of rows and columns also will be copied. So but now our destination image has just few number of columns, so instead of that we need to call create method only. So there are 2 steps we have combined: gdal.getDriver by name gtif, then create, then subset.if, we want to give it the name subset.if. Then anyway we have columns, rows we have calculated already. So and one band is there in our image, so this we are copying, and projection is same as our source image, so we are just copying from that image. And geotransform anyway we have modified, so we are writing the modified geotransform to the subsetted image. Then same thing, get raster band 1 and write array, then flush cache. You can see that there will be a subset image created here. So this subset image is created here that you can, that anyway we have visualized. Suppose if you want to visualize with any other software also can be done. So this way you can subset any image, if you, any image for your area of interest, if you know the coordinates of your area of interest. So this way we can subset our image using very easily using GDAL. Next thing is resampling a raster. So resampling means changing the spatial resolution of a raster data set and getting the values and set the rules for aggregation or interpolating the values across the new pixel size. Because if you change the resolution of your image, so then you need to get some new values using interpolation. So there are multiple resampling techniques. You can use nearest neighbor, bilinear, cubic, and so on. So there are multiple ways to resampling. So what is resampling? So this was our original image. Now suppose if you want to make it a coarser resolution, like 3-4 pixels, you want to 3-4 pixels you want to make a single pixel. So you want to make the image coarser resolution, or you can make a finer resolution. So you can decrease the pixel size. So both way it is possible. So let us see how do we resample an image using GDAL. Similar thing, we have first to have an image name. So we can just first open the image. Then we are fetching the first band, then reading the entire data from the image. Then this is the shape of my image. So this my image is 1151 by 1151 size. This has read the entire image. Now for suppose if you want to resample the image, now we need to call the, now suppose if you want to reduce the pixel size. So suppose if your original image resolution was 1 meter, now you want to resample it to 0.1 meter or 0.5 meter. So 1 meter to 0.5 meter. So that we will call finer resampling, or reducing the size of the pixel. So for that the function, similar function band.read array. Actually band, if you can explore more about the function read as array. So it takes multiple arguments. So dot read as array, it takes another argument, buffer x size, then buffer y size. So the entire image has the size of 1151 and 1151 rows. So buffer size x, there is an argument buffer size x. So your original data to which, so to the original data to how many pixels you want to fit once again. So that is like 1151 pixels. Now we want to make the pixel size half. So suppose initially our image was having 1 meter resolution. Now suppose if you want to make it 0.5 meter. So what will happen? The extents of our image remain same. Now what will happen? The number of pixels will get doubled, because we have reduced the pixel width by half. So now in the same area, number of pixels will double. So there we need to pass the argument buffer x size as 1151 into 2. So 1151 pixels we are converting into 1151 into 2 pixels. So similarly on the y also we are converting into 2. Suppose if you want to change the pixel size, you want to make it to 1 by 3. So if you make pixel size 1 by 3, the number of pixels will triple. So you need to pass it at 1151 into 3, 4 and whatever you want to, whatever the new resampled pixel size you want to change. Accordingly you have to change this buffer x size or buffer y size. The next argument you can pass is that resampling algorithm. What resampling algorithm you want to use for calculating the intermediate values which were not available but new cells values. So this way we can resample to the higher resolution, or similarly suppose instead of decreasing the pixel size you want to increase the pixel size or make it coarser. So 1151 image, now we want to make it out of 115 pixels, we want to take from that, we want to increase the pixel size so that now only 1151 pixels get converted to 50 pixels. So similarly we can make it a coarser resolution And then algorithm. So instead here we have used bilinear. Here we are using nearest neighbor. So this way we can resample our image. Now let us see how the resampling changes our images. So now we have three images. One is our original image. One is the image with final resolution, means we have reduced the pixel size. Reduce the pixel size means number of pixels will increase. And another is where we have increased the pixel size, so the number of pixels will decrease. So that will be a coarser resolution image. So this way now we are plotting three things. So here you can see this is our original image, and this is the resampled image to higher resolution. So here you can see that this has 1151 by 1151 pixel, but here more than 2000. So but there is no additional information we are retrieving because we are just resampled, and this is the coarser resolution image. So 1151 by 1151 image we have converted to a 50 by 50 image. So this way, using a read as array function, we can resample our image, and we have the choice of which resampling technique we want to use. So this is the with this today's lecture is completed. Thank you very much.